So, we are graphing polynomials by hand, an introduction today. So, one thing that you need to know about polynomials, they follow a very interesting pattern. If I ask you to graph y equals x, do you remember what that looks like? It's a straight line, right? So if I have my axes and I graph that, it's a straight line. It actually goes right through the origin. Yep, it's just y equals mx plus b, right? B is 0, your slope is 1. That's that perfect line straight through the origin. Okay? And then when I asked you to graph y equals x squared, do you remember what that looked like? It's a U, right? It's a parabola. So those are U shapes. And this particular one, the parent function, does also go through the origin. It's a nice U shape. Looks like that. You know what? Maybe we should do. So these are your parent functions. If I were to graph another line that was just to the first degree, right? Any straight line, right? They're just going to look, I don't know, something like that maybe. Or maybe I have one that goes down. So all of these graphs would have an x to the first power. Right? That's how I get straight lines. That's why that degree is called linear. Right? Because they produce straight lines. So let me graph a few of other ones where you have a quadratic, where you have an x squared. Because they don't always have to go through the origin, right? You might have one that looks like this. You might have one that looks like this. Maybe it's upside down and it never touches the x-axis. Right? So I have a bunch of different graphs that could come out, but all of these would have an x squared. There'd be degree 2. They are quadratics, hence why degree 2 is called quadratic. Okay, so you've learned all about these, throughout your math career so far, and we're now just starting to talk about higher exponents, so like an x to the third. If you graph the parent function, it looks approximately like this. It's going to come up from the bottom, it passes through the origin, and then it just goes up. So it kind of just does this funny little squiggle. But if you had other x to the third graphs, they could look something like this. Or maybe you have one that's upside down, and maybe it looks like this. Y equals x to the fourths. What do you suppose those look like? I mentioned briefly to you last week what some of them look like. They can be W's. If you graph y equals x to the fourth itself, it really just kind of looks like x to the squared, except it's a little bit more flat looking on the bottom. In fact, I'll put them on the calculator so you can kind of see. So it's very similar to y equals x squared. But other x to the fourth graphs can look like W's. Or if it's negative, you might have an upside down W. So real quick, let me just throw them on a graphing calculator so you can see if I had a graphing calculator. Okay, x squared and x to the fourth. Okay, so just so you can see what these graphs look like. So the first one that's going to come up will be the x squared, and then it'll do the x to the fourth graph. So there's x squared like we're used to. Did it go too fast? Probably. Hold on. Let me. So there's x squared, normal x squared. And now let's add the x to the fourth. I don't know if you can really tell, but it's a little bit flatter at the bottom. Maybe if I zoom in. Let's do zoom in. There's x squared, and there's x to the fourth. See it? Do you see how it's kind of... There's x squared, and there's x to the fourth. So, anyway. But, so, back to these cubic graphs. They can look like W's. Or some variation of a W. Okay? Or they can just look kind of like a flattened parabola. And I wish I had more room on this paper, but I don't. But if you did an x to the fifth graph, so y equals x to the fifth itself, as it is, it's very similar to x to the third. It's just a little bit more flattened. But other ones could look like, you ready for this? They could do this. So many wiggles. Or they could be like that. Or some variation of these. These sort of small peaks and valleys could be really high, really small. They could be almost flat looking. But the point is, I want you to recognize that there's a pattern going on here. So if I let's see if I can zoom out and get all of these in at once. What do you notice about this graph, and this graph? Anything? What do these three have in common? Okay, let me ask this question instead. What do these two have in common? Okay, let me tell you the answer I'm looking for, and then we'll try. I want you to look at the ends. The end behavior is what's happening to the ends of the graphs as x continues to positive and negative infinity. So in other words, as these x's get bigger and bigger and bigger in each direction, what's happening to these? Well, they're both going to go up forever. The same thing happens in the x to the fourth graphs. As x gets bigger and bigger in the positive direction or smaller and smaller in the negative direction, doesn't matter. The y's, the ends, are going to continue to go towards positive infinity. They're just going to go up forever. So what do you suppose y equals x to the sixth would do? The same thing or something different? Thank you, the same thing. If it's an odd exponent, they're going to look like these. If it's an even exponent, they're going to look like these. Look at the ends. The ends are what we're worried about. See how this one is going to go down to negative infinity. This one's going to go up to positive infinity. So is this, and so is this. All the odd exponents, they're going to do the same thing. They all come up from the bottom, do some business, and then they shoot off to positive infinity. All of them. You could do x to the 11th. Doesn't matter. Any odd exponent. If that's the degree of the whole thing, right? Because to get these other weird ones, I mean, there's a lot of other stuff that's going on. There's other things, like, for example, I have no idea, but this could be the graph of y equals x to the third minus 2x squared plus 15x minus 6. I have no idea, but the degree is to the third. And since the degree is to the third, I know some things about the graph before I even start it. I know this side's going to go this way, and I know this side's going to go this way. What I don't really know is what's happening in the middle yet. I know some things that are going to happen in the middle eventually, but right now I'm really just focusing on the end behavior. So the ends are always going to do the same thing if it's odd. And if it's even, they just both go up together. Well, Miss Sabia, then how'd you get these down here? They're both going down together. How do I get a graph that looks like this? Yes, your leading coefficient has to be negative. If that lead coefficient is negative, remember, that's how you got down like a frown. Well, it affects all the other polynomials the same way. So if I had a negative coefficient in front of a x to the fourth graph, they'd both go down together instead of up together. Does that make sense? Kind of? Sort of, maybe a little bit? Okay, so here's what we need to do. If we look at the sheet that I just gave you, let's start with an easy one, like, let's start with 4. 4 is a nice, easy problem. So we actually just talked about, if you read the directions, there's 4 things that we need to find. For each function, 1, state the maximum number of turns the graph could make. 2, determine the real zeros and state the multiplicity. 3, list the x-intercepts where the graph crosses the x-axis and where it does not cross the x-axis. We'll get to that. And 4, describe the end behavior. What I just talked to you about was the end behavior. So we can answer number 4 for, believe it or not, all of these. Yeah, so here's how we're going to write it. So let's look at number 4. What does number 4 look like? That's a parabola, right? That's a U-shape. So if I were to just, I have no idea what's happening, but I know it's a U-shape that's up like a cup. Don't I know that? Right? So if you're going to describe the end behavior, here's how we do it. Okay? So you're going to write, so this is really the answer to number 4. As x approaches negative infinity, what's happening to this branch? Yeah, so as x goes into the negative infinities, y is going to positive infinity. That side's going to go up forever. As x is going to positive infinity, this side, what's happening to the y? Isn't it also going up? Right? Right? This side's going up too. So this y would also go up to positive infinity. Does that make sense so far? Or no? Have I lost you? Okay. Let's try 6 then. We'll come back and do parts 1 through 3 later. But let's just get the end behavior squared away. So, as x approaches negative infinity, this is an x to the 4th graph, but it's negative. So what does it look like if I just sketch it real quick? Yeah, it could look like a W, or it could just be a parabola. It doesn't matter. The end behavior is going to be the same either way. So even if you made it a W, it's down because the lead coefficient's down. So as, really, when you see this, x approaches negative infinity, that's just a fancy math for asking, what's the left-hand side doing? So the left-hand side is going to, it's going down, right, on the left-hand side? So that's just going to negative infinity. So y is going to negative infinity. So as x right, as x, the left-hand branch, as x is going to negative infinity, is this guy. The y value is going down. What's happening as x goes to positive infinity? What's happening to this y? So that's the right-hand branch. He's going negative. That's it. Let's try a trickier one. Let's try number 3. Here's an x to the third, and the leading coefficient's positive. Yeah, sorry. Whoops, there it is. All right, so now if we look back at 3, notice I don't even care about all this other stuff. I don't even care all this business. It doesn't matter. I just, right now, care about the exponent and the leading coefficient. The rest doesn't affect the end behavior at all, okay? So if I look at number 3, I only really care about the fact that it's to the third power and the leading coefficient's positive. So what does it normally look like? They come from down below, they do some business, well, they usually just do that, and then they go up. So again, I don't really care too much about the middle right now, I just care about the ends. So, as x approaches negative infinity, or fancy language for left-hand branch, what's the left-hand branch doing? That one's going down. Because that's when x is going in the negative direction, is that way. And then when x is going in the positive direction is the right-hand branch. That's it. My y is going to positive infinity. It's going to be the same thing for every single odd exponent. As long as the leading coefficient's positive, they all have the same end behavior. It's the junk in the middle that changes. Every even one is going to have this same thing. They're just going to change the junk in the middle. The only way it's changed is if I have a negative leading coefficient. So that's why in 6 we flipped it over. So without me telling you what to do, try 1. Same as 3. Remember, all the odd ones are the same. It's just the stuff in the middle that will change. But right now we don't care about the stuff in the middle. We only care about the ends. So all of the ends are the same for all the odd exponents. 1, 3, 5, 7, 9, and forever. They all have the same end behavior. So you're going to tell me as x approaches negative infinity, what is y doing? And you're going to tell me as x approaches positive infinity, what is y doing? Okay, we got answers? Now be careful, this one has a negative leading coefficient. So it's really gonna do this, right? Some business in the middle I don't really care about, but because it's negative, it's all flopped over. Did you catch that? Be careful. So now that you see it, the left-hand branch is going to do what? Positive infinity, and the right-hand branch goes to negative. Okay, you ready to play a little game? Well, we're gonna. I think so. I hope so. Okay. You have a left arm and a right arm. You're going to show me with your arms the end behavior of the function that I say. You've played before? Okay, ready? Oh, well, I guess we can stop the video because I can't see this anyway. Well, no, well, they'll do it. I'll speak audibly, and they should play along. Okay, folks at home, ready? All right, so let's say the graph were y equals x to the fourth. What would the ends do? Yes.
I'm killing it 1 for 1.
They would both be going up, right? Right? Yes, that's what I want you to do. Show me with your arms what's going to happen. Y equals negative x to the sixth. Yes, it's an even exponent, so they're going to be doing the same thing, and they're both going to go down. All right. Y equals x to the third. So x to the third, you should have your left arm down and your right arm up.
I was doing it to your left. That's my excuse.
What about y equals x to the seventh?
I can't believe it.
Do it.
Wait, hold on. Yes, my notes.
Same, right? It's the same. Same. Y equals x to the 10th. Even, right? So they both go up, right? Y equals negative x to the 5th. Negative x to the 5th. I hope you're doing this. Your left arm should be up and your right arm should be down. Y equals negative x to the 100th. Negative x to the 100th. Both hands down.
You?
Yes.
Go on.
Ow.
That's all I heard.
Okay, so, end behavior. We get it?
Let's keep playing for 9 more minutes.
9?
Wait, what's your green one?
3.
I always mess up 32 and 25.
Oh.
One just said 25. And half ends at 32.
Oh.
It's like, how do you
I thought you meant like on the clock. Okay, gotcha. Well, let's fill in some more of these. How about number 2? As x approaches positive, oh, we've been doing negative first, sorry. Can I do what?
bring paper?
So, really, remember that's asking you, what's your left hand doing? Is it going down or is it going up? Your left hand.
Is it up, down?
This is your right hand. What's your right hand doing for this?
Down also?
The only time that they're going to do the same thing is if the exponent's even.
So it's going up,
Right.
which is what I said.
Okay, jump to 5. All right, so what is your left hand doing on number 5? Is it going up or is it going down?
I mean down.
Down. What is your right hand doing?
Positive.
Yes.
4 for 4.
Remember, if the exponent's odd, these two things have to be opposite. The only time they're going to be the same, the exponent would have to be even, because they're either going to go up together or they're going to go down together. If it's odd, it's 1 and 1. Okay, so you try 10 without me telling you what to do.
Does the fact that it has a form, does nothing?
No, the sign just matters. Because it's positive, you know what to do. It doesn't matter that it's a 4. It just matters whether it's a positive or a negative number. Good question, though. That's funny that the other ones don't have any. None of them have that. So, this is an even exponent. So that means these two answers are going to be the same. And what are they? They're both going up to positive infinity. Yes. Okay, if you want to finish doing end behavior for 7, 8, and oh, never mind.